Hello and welcome everyone. I am Professor Supriya Bani from Assistant Professor of Ramdev Baba College of Engineering and Technology and Management, here to give you a brief analysis of pre-processing of medical images. So today's topic is pre-processing of medical images. What is medical imaging? We have to process the different type of medical imaging techniques to do the analysis of medical imaging. So, medical imaging is the study of medical images is concerned with interaction of all the forms of radiations with tissues. The development of appropriate technology to extract clinical useful information, usually in the form of an image from the observed technologies. The first process is to define the image acquisition, where we have to download or acquire the medical image from the different sections like MRI, medical scans, ultrasound, CT image. These are the different image we have to acquire. Then we are going to use the data processing technique to filter this data for the further processes. So what is data processing techniques? The data processing, filtering, registration, data detection, finding objects and the organs and nodules. The third one is segmentation, extract, the delimitation of the object, and fourth one is the analysis of measurement, volume, curvature, and the fifth one is classification and diagnosis. So these are the different type of data processing, or you can say the image processing techniques, where we have to learn or understand the pre-processing techniques of the medical images. What is the pre-processing techniques are? Where we have analyzed the original and enhanced image. What is the pre-processing? Pre-processing is basically filtering of the image. It means if your image is not in the form of processed further, we have to analyze, we have to use the pre-processing technique to convert this process into images to form the enhanced image. Means you have an original image and you have to enhance this image for the further processing. What is the detection? Find location of object of interest without prior knowledge about their location, existence, bone, organ, polyp or colon, nodule in the lungs. If you are going to find these type of object in your image, that could be MRI, CT, ultrasound. So these detection can be defined your object is present in your medical images. What is segmentation? Exactly delimitation objects once they are detected, like vessels, liver, cardiac imaging, left ventricle, brain. These all are the object. Whenever you have applied the segmentation in this process, you have to find your object, you have to segment your object with the different type of similar pixels. It means it segment your picture with the different type of different distance of the pixel values. What is analysis? Measurement volumes, growth vessels, stenosis functional imaging strokes, cardiac perfusion, tumor perfusion, cardiac function, LV motion, injection fraction. In this way, we can analyze with the segmentation and object detection. Then the previous analysis is going to use your upcoming analysis. If your tumor has finded 2 or 3 days before, and after 2-3 days you are going to use your MRI image analysis, you can see the growth of vessel or growth of tumor has been increased. So this can be detected with these algorithms of image segmentation and image detection. Likewise, cardiac performances, if the liver is swelled, you can easily detect it with your MRI or your CT scan images that the liver size is slightly increased with the previous one. So these type of analysis can be done with your analysis of image processing with preprocessing, detection, segmentation techniques. In the taking the image, often underexposed or overexposed, the system we have developed can do the addition or reduction of the pixel intensity value so that it can turn a normal image into overexposed or underexposed and vice versa as in figure. Here we can see the first one is the original image, the second one is the overexposed image, and the third one is underexposed image. What is overexposed and underexposed image and why we are going to use this? So, if we are going to analyze the medical images and we have to segment images, these are going to pre-processed the technique for input image. What is pre-processing? We are going to filter our input image in the form of overexposed and underexposed, where we can see in the overexposed all the gray background is converted into white image, that is going to in the gray scale 0 to 255 more than 255, and when we goes with the underexposed image, we can see the gray sculpt images are converted to black images, that is considered as more the side of 0th pixel. So, in this way, we are turning our grayscale levels with the overexposed and underexposed images with pre-processing techniques. In taking images with the camera, noise always occurs, with results in the image becoming not smooth. The system that we developed can filter so that the image becomes smooth as in figure 4. A smooth image has a weakness, that is a blur at the edge. So, it is necessary to sharpen the edges boundaries with high frequency filter as given in the figure. Edge detection is a medical image processing technique that is widely used, for example, to find out the contour of a network and to estimate tissue area. This system can do site detection as well as in showing with the figure quality. Here we can see the smoothing of image, sharpen of image and edge detection. In the figure 4, you can see that the image could slightly going to blur to detect the noise or to remove the noise from the image. What is the basic purpose of smoothing the image? You are going to lower the intensity of the pixels. It means the colors, the areas, it could be detected clearly, but in the form of smoothness. The contrast is getting slowly low for this, because the extra additional and noises objects can be blurred with this smooth image. The fifth one is sharpened image, where we can see the sharp images can be detected with high intensity value. The colors are as it is same with that original image, but the pixels are very intense and showing each and everything with this sharpened image. The sixth one was the boundary image, where we can see the boundaries of all the portion like skull and their inner portions are correctively formed with the boundary function, and you can detect the boundaries for your original images. I will explain how beautifully medical images can be pre-processed with simple example to train an artificial intelligence model, and how data is prepared for model to give the highest result by going through the all pre-processing stages. The data I am going to use is bunch of 2D brain CT images. They are in DICOM format. You can simply apply this operation to your own data to get more efficient results for your model. Computer tomography is a scanning that takes image of X-ray which are sent to the body from different angles and combined using a computer processors to access cross-selection image like slice of bones, blood vessels, and soft tissue in various parts of the body. This image provides more detailed information than regular X-ray image. That's why we are using this computer tomography, because there are the new image sensor that slice can be used to analyze more effectively of your body parts and organs. In this way, anomalies in the bones, veins or tissues of your patients are detected. That's why more precise diagnosis can be made for patients, and the treatment would continue accordingly. Now, let's talk about what is the DICOM format. DICOM is an acronym of Digital Imaging and Communication in Medicine. Files in this format are most likely saved with a DCM file extension. We have to always convert our medical image to going with all the processing techniques with DICOM file extension with DCM. DICOM is both a communication protocol and a file format. This means that a patient can store medical information such as ultrasound and MRI images along with their information in a single file, while PNG or JPG files contain only name, date, number of pixel of the picture. DICOM format includes the patient's information, windowing, intervals of the pictures, which we can metadata. We call this metadata because all the data of the patients can be stored by this DICOM. So, we are not going to use the normal PNG and JPG format for the further process. That's why I am talking about this DICOM, which have to be used for the data contents. Briefly, it includes more detailed information of patients like their images, their data, their name, date, all the types of information can be stored in this DICOM format. This format not only keeps all the data together but also ensure that the information is transferred between devices that support the DICOM format. I have taken some few DCM images from the Kaggle dataset, and you can also take here from this. So, the import PYDICOM, this is the import library of DICOM which have to use for the maintain of this filing or format of DICOM. So, we have to consider the file path for the same, where you have to store all the images, all the data where the PYID DICOM is used. So, medical image can be converted with this PYDICOM dot read file and then file path, where you have to store the data with the file path. We have to give this code, then print that medical image. Now we are going to load the images in this format of DICOM and retrieve the image or print the image with this print medical image format. After the basic summary of computer tomography and DICOM, let's move on with the pre-processing. I used 5 steps during the pre-processing stages of images. These steps are transforming the HU, removing the noises, tilt, corrections, crop images and padding. These majorly 5 portions are going to pre-process your image or your normal image to your enhanced images. After applying these pre-processing steps of data, we see that model accuracy got increased significantly. I am about to explain the pre-processing methods. To see the code in clearly format, you can go to the format code with, you can see how we can going to use this pre-processing techniques with this code. After loading our images data in DICOM format, we will transform it with the Hounsfield unit form. Now, transforming the HU form. The Hounsfield unit, that is HU, is a relative quantitative measurement of the intensity of radio waves used by radiologists for better explanation to understand the computed tomography images, that is CT image. The attention and the coefficient, the absorption of radiation within a tissue is used during the CT reconstructor to produce a grayscale images. The linear transformation produces a Hounsfield scale that display as a gray tone. More dense tissue with greater X-ray beam absorptions has positive value and appears very bright. Less dense tissue with less X-ray beam absorption has negative value and appears dark. The Hounsfield unit is named after famous Sir Godfrey Hounsfield, who has part of the invention of the computer tomography and was awarded with the Nobel Prize for it. We can obtain the HU by using rescale intercepts and rescale slope headers. Here we can see the transform HU of medical image, that intercept medical image dot rescale intercepts and slope with medical underscore image dot rescale slope. Now we have finding the HU image with the combination of image, slope plus intercept of image. Now with returning HU image, we have find the all HU image considered with the slope and with the rescaling of intercepts. If you want a specific zone of the image, you can adjust the windowing of the image. How can we adjust the windowing? So, window image, we have to set the center of window, window width, then window's center. We have to calculate the image window and its width by including its center. Then we have to copy this window image in our original image and finding the minimum and maximum of these windows, and finally we return the window image with finding the center, maximum and minimum of that window. The next step is removing noise. Now, during pre-process, removing noise is a very important stage. Since the data is improved after the implementation, we can see it more clearly. So, model can be trained better. Here we can see we are going to do the remove noising with this form of image, where we have done already the HU processing and the windowing processing. Now we are going to use the image smoothness, enhancing the image contrast, and with the blurring image we are going to use this noise removable from the major image. Here we can see the original image is with us. When we are going to use it with mask, and after masking, the final image can be converted with the higher intensity values, the HU calculation, the window calculation and the noise removal calculations. Another part is your tilt correction. Now what is tilt correction? Tilt correction is an alignment of brain image in a processed way. When tilt expression by brain CT image, it may result in misalignment of the medical application. It is important because when we train the model, it can see the whole data through the same alignments. Now again we can see this is the original element of image, that is in the form of tilted, and we have to mask with this tilted eliminations. So the tilted width, height, center windows, HU are all collectively analyzes with this tilted form. Now we are going to analyze our final image even in though this is also gained with a tilted form. So the tilt analysis or tilt correction of the images is very important for their height, width and center evaluation. Manually correcting the tilt on a large scale data is time consuming and expensive. Thus, there is a need for an automatic way of performing tilt correction in pre-processing before the training, because before the training we have to process the images with the all angles. It will slightly tilted in left or slightly tilted in right, but the picture is similar. So the pre-processing technique is going to use this with tilt correction that could not be done manually for a large data set. So this is going to a pre-processing part or pre-processing step that could be containing the tilt correction for all the medical images. Now this is the code to tilt corrections, where we can see the X top, Y top and X board and Y board, where the math corrections of angle can be decided of tilted angle if angle is greater than 90, and if angle is equals to or less than 90, we have to shifted it plus or minus of the angles, and then we could define what is the coordinates are given their height, width, their center and their angle corrections. So after detecting the tilt angle detections, we can correct in the form of the major or analyzed image, as the image can be tilted here and tilted here. So the main image can be converted in the final image with the correction of tilt. Here we can see in the image, the first input image is tilted into right side almost in the angle of 25% or 25 angular sides pe, and we have to find the almost corrected, or we can find the all straight or corrected tilt corrected images in our final image with this pre-processing techniques tilt corrections. Now the again next step is crop image and add pad. Cropping image is needed to place the brain image at the center and get rid of unnecessary part of image. Also, some brain images might be placed in different location within general image. By cropping image and adding pads, which will make sure almost all the images are in the same location within general image itself. Here we are going to use the crop image function, where we are loading the image in the crop image function, then we have to use the mask for the image, and then we are going to analyze the coordinates which have to apply the array fields, top left and bottom right approaches, where again we are going to use the coordinate of with axis x and axis y. Now we have to crop the image with left to right, bottom to up approach, and finally the return is the crop image, where we are going to use cropped image from left to right and bottom to up, and cropped images is returned by this code. Normally we defined the final image with zeros functions, with coordinate function, with their height and width function. So the left and top can be decided with this cropped image, and when we get the final image with this all pre-processing techniques, then we could define cropped image, HU analysis, then height and width coordinates, windowing analysis. These analyses have been done with the pre-processing techniques. Finally, we got this padded and cropped images with the final image, and if we have seen the original image, that could be a major portion of the cropped and intense and highlighted images can be there with the padding of extra extra coordinates of h and y. Here is the result, a clean, corrected and centered brain image ready to go inside the training. Now I am going to discuss the CT image pre-processing steps. Here is a quick summary of the processing steps required, which more details provided in the subsection. Stack up the CT slice in the right order. Double check that the CT scan is the desired orientation. Convert the pixel values to Hounsfield units, that is HU, using DICOM. Attributes, rescale slope and rescale interprets. Clip the pixel values to -1000 HU to +1000 HU, the particles lower and upper limits of the HU scale corresponding to the radio densities of air and bone respectively. Use simple ITK to resample each volume of 0.08 cross 0.08 mm to enable a consistent physical distance, meaning of 1 pixel across all patients. Convert the pixel values to 16-bit integer and save with lossless zip compression to reduce the storage requirements. Now, rescaling pixels values to Hounsfield unit. A CT scanner's measurement are represented with Hounsfield units. Hounsfield units indicates the radio density of material and range from approximately -1000 HU, that is could be containing as air, to +1000 HU, that is containing as a bone, with water in the middle at 0 HU. In some cases, HU can reach around +2000 for very dense bone, example cholera in the air. But most tissues are in the range between -600 to +100 HU. Resampling, in addition to ensure that the pixel values have consist radio densities measurement across the whole data set by converting to Hounsfield unit, it is also important to ensure that each pixels represent a consistent volume throughout the whole data set. A DICOM header includes the attribute pixel spacing, which includes an X measurement and Y measurement in millimeters like X spacing and Y spacing. The Z spacing space can be interfered by subtracting the Z position values of adjacent slice reported. In image position patients, dot take together XYZ spacing indicates the physical volume of cubic millimeters that can single Volvex voxel that represents a voxel in 3D pixel. It means whenever we calculate the x, y, z 3 coordinates, that is considered the voxel in the 3D pixel. So we are considering here the 3 coordinate spacing here. Now I am going to discuss with you the pre-processing of MRI scan. Pre-processing an MRI is an important step towards making it suitable for training. To pre-process a scan, we will be using MONAI, that is Medical Open Network for Artificial Intelligence, MONAI. MONAI is an open source framework for accelerating research and development in the medical imaging. It was built on top of PyTorch and Resales under Apache 2.0 licensed. It is useful if you chain a series of transform. You can import compose from MONAI transforms. It will store a sequence of transform applied to an MRI scan. First, let's get started with loading and visualizing a flare, that is fluid attitude inversion recovery. Modality along with the ground truth label from a patient's brain tumor MRI scan. A patient's brain MRI scan contains 4 different modalities, that one T1, T1 weighted, T2 and FLAIR, along with its ground truth mask localizing brain tumor. PyTorch accepts channels first input. For instance, if your image shapes is 640, 643, you should convert it to 3, 640 and 640. An MRI scan consists of 4 channels. Therefore, we must ensure that it has channel first input. To do so, we use ensure channel first D from Monai transform. Sometimes it seems nice to have consistent orientation for all axes. The default labels are left, right, posterior and anterior and superior. The following Monai transform will change its orientation to have a posterior, left and anterior PLI. Now, the resample to a contrast voxel size. The input volume has different voxel size. The following transform normalizes the voxel to have 1.5, 1.5 and 5 mm voxel size. Random affine transform. This affine transform combines skewing, transform, rotation and scaling in the following affine transform. Take a volume and it applies a set of geometrical transform with some probability. Random elastic deformation. This particularly alteration is additionally beneficial for expanding data. It shares similarities with affine transform and it operates on a volume. Within this modification, the smoothness of the distortions is regulated by the single range, while the amplitude of the distortion are controlled by the magnitude range. Monai has all the transform that you may need, or you can design your own transform. In conclusion, we saw how to read, write and process an MRI images in Python. Furthermore, we saw ways to pre-process an MRI image using open source framework Monai. Now, I am going to conclude this pre-processing technique of medical images. It can be concluded that the Python programming languages and the OpenCV library can be used for medical image processing with very good results. Image processing operations such as image enhancements, noise removal, site detection, contouring and segmentation can be done very well. With its open source nature, medical image processing can be done at a very cheap price using Python and OpenCV. Thank you.